Now that we have discussed in detail about MOS behavior, MOS large signal and small signal behaviors, let's start building our amplifier, our first amplifier. Okay, so as I said, in order to build an amplifier you need certain design parameters, or you need some constraints, or you need some kind of inputs. Something should be given to you so that according to that specification you will build an amplifier. So let me give you a constraint that I want voltage gain. If I write AV, it basically means voltage gain. Okay, so this should be 10. Okay, and I am saying it should you should get this gain across a load resistor of 10 kilo ohm. Okay, this is something that I am giving to you, and you are allowed to use a MOS transistor and whose Kn into W by L, this is process parameter, which is 500 microamp per volt square. This is what we had been using so far, and then your transistor will have a threshold voltage of 1 volt. Okay, so these are the information that you are supposed to know. And as per our discussion in the last lecture, that so this MOS transistor in its native form, the incremental equivalent will look something like this: GM VGS, while this is VGS, G and S. Okay, and then here is where you give the input, and here is where you take the output. Okay, and if your input source is given in this way, and then if your load is connected in this way, then you are going to get a gain V0 by Vs, where this is V0. Okay, minus GM RL. Okay, this is something that it's a simplistic assumptions and considerations which will lead you to this gain. Okay, so here mod of this gain is 10, so here also I can assume mod. So this basically means that AV is equal to GM RL equal to 10. Okay, this is what is given to me, right? And RL I know is 10k, so I can find GM as 10 by 10k, which is equal to 1 millisiemen. Okay, this is Siemen is the unit of conductance. You can even say that is mho, but it's up to you. So this is 1 millisiemens. Okay, now you know your GM. Okay, so GM expression is something that we had discussed earlier, because see, finally where we are getting at, we have to build the transistor and give its operating point, right? That is what we have to figure out. These are small signal, this is small signal gain, and this is the load resistance that is given to me, and then I have to figure out how to operate the transistor. So what is the operating point that is supposed to be chosen, and all these things is something I have to figure out, right? So now so I'm I'm in the process of finding out the operating point, and then I know that my GM is having an expression Kn W by L into VGS minus VT. By the way, I hope you still remember the fact that Kn is nothing but mu1 times Cox. Okay, so this is the expression that I have in my hand, and I can use any expression for GM, but then it appears as though this is useful for the purpose of calculation that I am going to do now. Okay, so Kn value is something that I know as 500 microamps per volt square. I am leaving away the unit, and W by L is 1 anyway, so Kn into W by L is this value. Okay, and then VGS is something that I have to figure out, and Vt is 1 volt, right? And this is equal to 1 millisiemen. So if you try to find out the VGS from this expression, because that is the only unknown, you would get 3 volt. Okay, so by operating point, what I mean is VGS, VDS, operating point. We need to figure out the operating points. That's what we started with, and operating points are ID, VGS, VDS. Okay, VGS is something that we have figured out. Okay, and to operate the transistor in saturation, I know that my VDS should be greater than VGS minus VT. Why I am stressing about saturation? Because this incremental equivalent is valid only in saturation, and we have assumed this incremental equivalent, and that's how we got this gain of GMRL, right? This is mod. Okay, so that is why we are getting it. That is why we are saying VDS should be greater than VGS minus VT for saturation condition. So if it is 3 volt, then VDS should be greater than 2 volt, because VT is 1 volt, right? Now only thing that is left for me to find is ID, and ID is nothing but Kn W by L and VGS minus VT the whole square by 2. This could be also written as Gm times VGS minus VT by 2, right? So this is Gm is 1 millisiemens multiplied by VGS minus VT is VGS is 3 volts, so 2 by 2 volt, so this is equal to 1 milliamps ID. So we have figured out ID also. Okay, so what we have actually figured out, we have figured out that DC operating points, in other words, if I represent that in circuits, okay, so it would be, I have my MOS transistor, okay, and this is the gate, this is the drain, this is the source, and if I ground the source, okay, which is what I want, okay, if I ground the source, then my VGS, if I give 3 volt here, and as a VDS, if I give anything greater than 2 volt, then I will have a current of ID flowing, and that is equal to 1 milliamps, right? This is what I have figured out. Okay, so this is the first step in solving or synthesizing circuits or solving any problem, to figure out the DC operating points or fixing the bias. Okay, but the obvious problem with this particular bias is that incrementally what I wanted is this incremental equivalent. Okay, this is what I wanted as incremental equivalent. The source should be grounded, and then I want some source voltage, some kind of signal to be given at the input, and some load at the output. But I don't have anything here like that. So if I don't have anything here like that, how my incremental equivalent would look like? It would look like this transistor's incremental equivalent. Every single element in this circuit should be replaced by its own incremental equivalent, and the transistor's equivalent is something that we have done over and over again. So this is the incremental equivalent. This is G, this is drain, this is S and VGS, and this is GM VGS. Okay, now this gate terminal, gate to source, I have a DC voltage which is a constant voltage, and we know incremental equivalent of a constant voltage is a short. Okay, so this will act as a short, and here also I have a DC voltage, this will also act as a short, which is of no use to me, because no input side is shorted, output side is shorted. What would I do? I mean, nothing. VGS equal to 0, no current will flow, no output, right? So ideally I cannot just like that connect things like this, or just connecting a DC only will not help me amplify anything. Okay, I should also connect AC signals. So how do I do it? So let me redraw the circuit again. So I have my MOS transistor, okay, and I will first step actually to synthesize the circuit is to picturize, or if to represent what exactly you want in the incremental equivalent. Okay, so incrementally, let me draw the incremental picture first. So in the incremental picture, MOS transistor I would represent in this way: GM VGS, well, this is my VGS. Okay, and I want to give some source. So this is the Thevenin equivalent of the signal source. whatever you are going to give at the input. Okay, and it's open circuited, nothing is there here. And then you have drain terminal, this is gate, and this is source is grounded. Okay, it is assumed to be grounded. Sometimes I may not even show, but it's assumed to be grounded. Okay, if it is not grounded, I will explicitly mention. And then you have to connect a load resistor here, right? So this is what I want as in the incremental picture. Okay, so see, this particular box here, which I'm going to show in the red pen. Okay, this particular box is the transistor. Is this transistor's incremental equivalent. Okay, like a diode had only one resistor because it is true terminal, transistor's incremental equivalent is what is shown in this red box. Okay, but sometimes when it is cumbersome to draw this over and over again, we may even draw something like this. We will just draw the transistor. Okay, or in some books you might see that they will say it's an incremental picture, and then they would draw a transistor like this. Okay, and then they would connect the load here, and source would be connected here. Okay, so it is still an incremental picture, and it is understood that you should be able to convert this to the what is in the red box. It is it's assumed that that in an incremental picture transistor's equivalent is what is shown like this. Okay, sometimes it will not be explicitly shown, and you should be able to understand when we convert from the DC picture. When you convert things to incremental picture, it is assumed that that this transistor will be replaced with this incremental equivalent like this, even though I draw things like transistor itself. Okay, it is assumed that this. Okay, so now this is the incremental picture that I want to connect some source, I want to connect some load. Okay, so I know that in incremental picture the DC voltage source will go short, and that is what we had seen in the last in the last discussion. We saw that it goes short, and that is the problem we had. So instead of connecting only the DC voltage sources, I would now connect my AC in series with the DC voltage source. Okay, this is Vs and this is 3 volt, and source as usual is grounded, and on the drain side I will put my RL. Okay, and then I will have my VDS. Okay, I will have a situation like this. Now see, in incremental picture this 3 volt will go short. So 3 volt short means Vs and Rs will appear at the gate and source side. No, so this is anyway grounded, source is grounded, so this is also connected to source only. Okay, and on the output side I have my VDS will go short, right? Because in the incremental picture this is short. All the DC voltage sources will go as short, right? Because their resistance value would be 0, and RL would appear from drain to ground, right? So this is exactly same as this one, right? So incrementally I have achieved what I wanted in the DC picture. Okay, in the DC picture my elements are connected in such a way that I would get the incremental picture shown here, right? It's simple as that. Now tell me, if this is 3 volt, would I still have my VGS to be 3 volt? Okay, that is the question. Okay, because now on and above 3 volts I have some other voltage source as well as some kind of a RS, right? But it turns out that the logic is that when you are doing DC operating point analysis, you short the signal source. Okay, you short the signal source when you are doing DC operating point analysis. So obviously when you short the signal source, you and one more reason is that Ig is equal to 0. There is no current that is flowing in, so there won't be any kind of voltage drop at all. All the 3 volt would appear at VGS. Okay, so on the input side you wanted VGS equal to 3 volt earlier, now also you have 3 volt even after adding Vs. But what on the output side? On the output side you said VDS should be greater than 2 volt, right, for saturation operation earlier. Now this is under under an assumption that ID will be equal to 1 milliamps, and I want ID equal to 1 milliamp, then only I'll get the gain of whatever I said on all these things, right? Now if ID is 1 milliamp and RL is equal to 10k, I am going to have 10 volt dropping across this RL in the direction that I have shown. Okay, 10 volt in this direction because current flows like this. So if I say VDS greater than 2 volt only, it will not suffice at all. What I was saying is that the voltage at this drain and this source, right, the voltage across this particular node and this source should be greater than 2 volt. But this voltage now, if it is, previously this node was directly connected to this node, right? Now there is a resistor, so this is already dropping 10 volt, so this should be greater than 12 volt for the drain source to be greater than 2 volt. Okay, this is no more VDS, this will be some VDD, some other voltage. VDS is only this much, okay, drain to source. Okay, so this is something, if you do in this way, then you will achieve the incremental equivalent like this. The current will be exactly what you wanted, and so on and so forth. Okay, so as I said, when you want to do some DC analysis or find out the operating point, say for example you can actually take this circuit and try to find the operating point, and then while doing it you can nullify this source or short the source and try to figure out the operating point. And when you are trying to calculate the incremental equivalent gain and all these things, you can actually short the DC voltage sources, and if there are DC current sources, you open them and then try to arrive at the incremental equivalent. Okay, so now is this sufficient is the question. I mean, we have achieved it, like whatever we wanted, this particular incremental picture which would give me a gain of 10, okay, mod AV is equal to 10, and we wanted a DC picture where we need to have a current of 1 milliamps, and then you need to supply the voltage of 3 volt at the gate source, and then more than 12 volt at the drain source. So you achieved everything, right? So is this sufficient is the question. It turns out that there are some problems with this implementation, and we'll discuss the problems. So the first problem is that single power supply. Okay, the first problem. So by single power supply, what I mean is that more often you will be having only one power supply for your circuit. Okay, so you might not be able to access 3 volt power supply as well as 12 volt power supply or 15 volt power supply or whatever. The best example would be your mobile phone or laptops, where you have only one battery, okay, and it should give you only one kind of voltage. And similarly, when you are working out in the lab, each batch will be given one power supply battery, right? So if you want to have two different voltages, for example, you cannot connect 12 volt to the drain as well as 12 volt to the gate. It will not work. It will not give you 1 milliamp that you wanted. So you certainly want to have a smaller voltage compared to 12 volt in some case. So you will take one, the maximum voltage that you need as the voltage in the battery, and then you will try to derive at the smaller voltages that you need for other circuit nodes, right? So the first problem is that you cannot access two voltages like this. You will be, you can actually supply different voltage to different nodes, but you should be able to do it with a single supply voltage. So certainly this configuration is not valid anymore. If I make the constraint that I have only single supply voltage, I don't have the freedom to access 3 volt somewhere and 12 volt somewhere here. So this configuration will not be valid. There should be some changes, and we will see what. Okay, second constraint is that, so most often you cannot access, no access to both the terminals of source and load. Source, load. What I mean by that is, sometimes the source for your in your circuit would be from the output of the previous stage, and similarly the load of your circuit would be the input impedance of the next stage. Okay, in that case you cannot just like that connect the next stage circuit. You cannot access both the terminals of the next stage circuit and connect across your the stage you are working on or your circuit. Okay, it's simply not possible. So the representation of the source would be the Thevenin representation, right? That is what we usually say. So you have some Thevenin voltage and Thevenin resistance, and this particular point is always grounded. You don't have access to this. What I mean by that is you cannot take and connect it in between your circuit like this. Okay, it's simply not possible. Okay, and there can be some previous stage whose output can be represented as Thevenin equivalent, whose one terminal is grounded, and you can access only this particular terminal, and this terminal should be connected as signal to your circuit. Okay, so you have to figure out how to do it. Second thing is, you cannot access both the terminals of the load. Load is just a representation. Okay, the load resistor is a representation of the load your circuit is going to drive, right? So it's not like a simple resistor. If it is only a resistor, you can always connect like this, but if it is not a resistor, one end of the load is always not accessible. It is connected to ground. You can only access the other terminal. So only one terminal can be accessed, and you cannot really connect both the terminals in this way. Okay, one should be always grounded. You should figure out how to do it. Okay, so these are the two main constraints for which you need solution to proceed any further for building amplifiers.